Good afternoon, sir.
Hi, good afternoon.
Yeah, happy Mahasaptami.
Happy Mahasaptami.
Are you Bengali?
No, I'm from Odisha.
Okay, okay.
So last time you asked a question related to the number of T states, right?
T
So
states, yeah,
yeah,
yeah.
so that
I have a
thing,
doubt on that.
yeah,
Hmm.
so that thing I'll cover today,
Okay,
and
okay.
yeah, so that's a very brief thing. So we will try to cover that, and probably it was not covered in the lectures, right?
No, 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 no. That's why I have some issues
Okay,
regarding
okay.
that.
Yeah.
Yeah. Hmm.
We'll wait for 2 minutes more, then we will
Okay.
start.
Yeah, okay, okay.
Yeah. Okay, I think we can start today's session. So,
Yeah.
meanwhile, when others are joining, so I'll try to address your previous query first. So, any instruction has two parts. One is the opcode part, next is the operand. So opcode is basically the instruction, means like move or add or something like this, which is actually telling you what to perform. And operand is the content on which that operation is performed. Okay. So when any instruction is being executed, so one thing that happens is opcode fetch, which by default takes 4 T states. In opcode fetch, what happens? The opcode that is present in the instruction, it is going to be fetched, and the delay associated with it is actually 4 T states. The next thing is memory read or write, that takes 3 T states. Okay, so let's say there is an instruction called move a comma b. Okay,
Yeah.
so this instruction is actually already present, means, so let's say the complete instruction looks something like this. Let's say 1011 something 0000. Okay, so there is a particular instruction assigned to move a comma b. Okay, so whenever it is going to be fetched, not only move is going to be fetched, but move a comma b as an instruction, it is going to be fetched as a whole. Okay,
Yeah. Hmm.
so in this particular case there will be only opcode fetch that will take 4 T states. But let us say there is an instruction mvi a comma 30 h. Okay, So there can't be a particular instruction which says that MVI A comma 30H. 30 is an immediate value. So MVI A will be there as an opcode. 30 is the operand. Okay. And 30H, it means there will be A, B, C, D, E, F, G, H. There will be total 8 bits. Right. So for each byte operand, so for each byte operand we will need 3 T states for memory read. Okay, and any instruction that is being executed, it will anyways fetch around it will anyways fetch the opcode, right? So that will cover 4 T states. So for this particular case, there will be an opcode fetch that will cover 4 T states plus, so opcode fetch includes this particular thing, MVI A comma something, okay, and plus there will be a 3T state to fetch 30H, to read the 30H from memory. Okay, so total number of T states required is 70.
Yeah.
Okay, similarly, let's say there is DCRC. So can you guess how many memory read operations, or what is the total number of T states associated with this?
4 T states, because only opcode fetch is there.
Correct. So similarly we can also do for, let's say, LXI H comma 1 2 3 4 H. Okay, so here can you tell me how many bytes operand is present?
16 bit and
Yes.
2 byte.
Correct, 16 bits or 2 byte.
2 bytes.
So 2 byte means how many memory read will be required?
2 times.
2 times.
Means 60.
Correct. So it will be 60, and LXI
and
H is
40 for opcode fetch.
correct. So the total will be
10.
10.
Okay. Yeah.
Okay.
It's clear
So
now.
this is actually the logic behind the T states calculation. Okay.
Yeah.
So similarly you can do for any instruction that you find. So actually most of the instructions can be taken care of by this method, but some other instructions like call and return, so you need to be very specific there. So it is better to take a note of those exceptions when solving the problems. These instructions you can figure it out from the number of bytes of operand and using the opcode fetch, right? Okay, so I think other participants have also joined, so we can start today's session. So today's session is mostly a revision of whatever we have covered so far from week 1 to week 12, and we will be going through the important problems that we have solved so far. And my name is Arpit, and I'm a PhD scholar from IIT Bombay, and I'm a TA for this course. And so far from week 1 to week 12 we have covered introduction to number systems, floating point representation, logic gates, sequential logic, combinational circuits, semiconductor memories, hardware description languages, and 8085. Okay, so let us start today's revision session, and if anyone has any doubt, then they can let me know. So we won't be covering all the topics that were covered previously. Okay, so one question popped up, I'll take it up. So we won't be covering each and every question that we have solved so far, but what we are going to do is we are going to cover the important ones. Okay, so for rest of the questions I'll suggest you to have a look at the previous session recording. Okay, so there was a question that came up. Please tell me indirect addressing mode. Okay, so indirect addressing mode. Okay, let me take an example of. Let me take an example here itself. So let's say there is something called as LDXB. Yeah. So LDXB. So that is one example of indirect addressing mode. So what will happen is, so BC register. Okay. So the contents of BC register, okay, will contain a memory. Okay, will contain a memory address. So that memory address will be actually containing some data. Okay, and that data will go to the accumulator, right? Because the data is not being called directly, but through the register pair, means through the memory that is present in this register pair. So it is being indirectly addressed, and because of that reason it is called as indirect addressing mode. Okay, so let us start today's session. So we'll start from week 1. Okay, so in week 1 we covered mostly conversion from one number system to another. Okay, so this was just an example, like if a decimal number given as 76 and we have to convert it into hexadecimal. What we need to do is, for hexadecimal we perform the long division method taking 16. Okay, so I divide 76 by 16. Okay, so 16 fours are 64, right? So 4 will come here and the remainder will come here. So the remainder is 12. Okay, and I have to arrange it in this format. So the last one that is obtained, that will come first here. Okay, and the remainder goes here. And how to represent what is 12? So 12 is basically after 9. What we do is we start using letters A, B, C, D, E, F. Okay, so if I assign the corresponding place for 12, so it is actually C. Okay, so 4C is the decimal representation, hexadecimal representation of 76. Okay, the next question is related to octal numbers. Okay, so if 651.124 is given in octal, we have to represent it in hexadecimal. So the first thing that we are going to do is, we will first convert the octal numbers into its equivalent binary using 3 bit at a time, because it is octal, so we will need 3 bits. Okay, so I convert 1 as 001, I convert 5 as 101, I convert 6 as 110, 1 as 001, 2 as 010, 4 as 100. Okay, after doing this, what I need to do is, okay, you place the decimal point. From the decimal point to the left, you start grouping the bits in a group of 4, because we need to convert it in hexadecimal. Okay, so I take a group of 4 bits here, and similarly I keep on doing this grouping till I reach a non-zero number. Okay, so I reach non-zero number at 1 itself, but it has to be grouped in bits of 4. So what I do is I append zeros to this one. Okay, so that is not going to change my value. So I just do that, and the same thing I do just after the decimal as well. Okay, so after the decimal point, I start grouping the bits in group of 4. After doing that, I just convert those bits into their equivalent hexadecimal. Like 4 zeros is 0, then I have 1010, that is 10, right? So 10 is converted as A. Okay, then 0010 is 2, 1001 is 9, similarly 1010 is A, 0001 is 1. Okay, so the next question is related to conversion from binary to octal. So here also we'll use the same strategy. You choose a group of 4 bits, sorry, you choose a group of 3 bits and convert it into decimal. So yeah, so I converted not converting into decimal, converting into octal, because here we are needed to convert into octal. So 010 in octal is 2, 001 in octal is 1, 110 in octal is 6, 110 in octal is 6. So 6612 is my desired result. Okay. So had it been asked that convert binary to hexadecimal, what you would have done is you could have taken a group of 4 bits. 4 bits here, 4 bits here, 4 bits here. Okay. Then it would have been something else, right? 1010 is A, and 1 and 4 zeros, it is 8. Then 1101, this is 13. So 13 is
D.
correct. Okay. Is it D? Yeah, it is D. So similarly, okay. So the next question is related to signed numbers using 1's complement. So here we were supposed to find the sum of the following negative numbers. We are given -10 and -5. Okay. So the first thing that we do is we just write the magnitude. Okay. In magnitude form, we have 1010 as 10 and we have 0101 as 5. Okay. And I get their 1's complement representation first, but before that we need to make it 5-bit, so I just appended 00 here. After that, for 1's complement, what we need to do is we need to toggle all the bits that are present. Okay, so I just toggled all the bits here. Okay, let me okay, so I just toggled all the bits here. Similarly, I toggled all the bits here as well. Okay, and after toggling all the bits, what I do is I simply add them up here. Okay, after adding these, so the result that is obtained is 1111, and there is a 1 carry. Okay, it means it's a negative number, so I can directly write it as -15. Okay, that is the answer to this question. Yeah, either -15 or else I can also write it in this format, -1111. So here what they have done is they have just separated the sign and kept the magnitude separate. So similarly you can also do, keep the sign separate and keep the magnitude as separate. Okay, so the next question was related to figuring out the number system in which it is being used. So the base of the number system. So we have 110x, that is equivalent to 132 in base 4. So we know that if any system is in a base x, then what happens is, starting from the 1's place to 10's place, you can write it in the form of x to the power 0 for this particular place, then x to the power 1, x to the power 2, so on and so forth, right? So the same thing we do here. So 0 into x power 0, 1 into x power 1, 1 into x power 2 equals, same thing here, 4 power 0 into 2, 4 power 1 into 3, 4 square into 1. Okay, we will equate both the sides. We will arrive at an equation like this. So this is a quadratic equation. We'll try to find out the solution of this equation. Okay, we will solve. We will get two values. One is 5 and -6, but -6 cannot be a base, so 5 is the answer to this question. Okay, so the next question was related to finding the equivalent of 6-bit binary number 101.101. Okay, So just like we do for the left side, for the right side of the decimal, what happens is each place has a value assigned with a negative sign, like -1, then it will be 2 power minus 2, then it will be 2 power minus 3. Okay, rest of the steps are same for the left side of the decimal. Okay, we just add them up and we obtain 5.625. Okay, so the next question is related to the number is given and we have to figure out its equivalent in base 4 number system. Okay, it is given in decimal to us. So for the left hand side, the number that is present, we go for the long division method. Okay, we perform the long division method by dividing it by 4. Whatever is the quotient and remainder, we just put it in this way. Okay, we go on dividing them till that number is less than 4. Okay, so once it becomes 3, it is less than 4, so we stop our division process there. Okay, so yeah, so one student asked me that when do we get to know when to stop the long division method. Okay, so the long division method stops when this number that you arrive at is less than the number that you are dividing. Okay, so after that what you need to do is same thing, you just need to arrange in reverse order 3, 2, 0, 1. So that takes care of the before the decimal place, whatever is the result for that. So for after the decimal place, like 0.4375 is after the decimal place number. So what we need to do is we need to multiply it with 4. Okay, we multiply it with 4 and we keep on doing the multiplication till this result is all 0. Okay, so there is a catch here. So there is a possibility that this result won't be always all 0. Okay, so in that case you can go for up to n places of decimal. Okay, like you can if it is given in the question up to 3 places of decimal, then you can perform the multiplication thrice, or else you can assume that to be 3 places of decimal if it is not going to end. Okay, you can figure it out that this multiplication is not going to give you 0, 0, 0 every time. Okay, then you can stop after calculating 3 or 4 places of decimal. Okay, yeah, so after multiplying whatever is the integral part of the number, okay, you take that one and place it here just after, right after the decimal point. Okay, then whatever is the remaining fractional part, so you take that like 0.7500, you multiply it with 4 again. Okay, and in this case we obtain 3.000, so 3 goes here. Okay, and 000 is discarded. Okay, the next question was related to computing the 2's complement form of -45. So the first thing that we do is we first compute what is the binary representation of 45. We go for the long division method. Okay, then again we take the reminders, okay, in the reverse order. But after taking the reminders in reverse order, we observe that it is total 6 bits, but we are asked to go for the 8-bit representation. Okay, so what I do is I just append 2 zeros at the front, because appending zeros won't change my value if I am appending at the front. Okay, and in case of a decimal, if I append the zeros after the end of like all the decimal digits, then it is not going to change its value. Okay, so yeah, after appending 2 zeros at the front, what I do is I get the 1's complement. Okay, so that is basically flipping all the bits. So after I flipped all the bits, to get the 2's complement from 1's complement, I just add +1, and whatever is the result is my 2's complement form of -45. Okay, then the next question was related to addition of hexadecimal numbers. So we have 2 hexadecimal numbers, DEF.12 and 12EF.C. Okay, so I just arranged them here. Okay, And for simplicity, what I do is I make a number line like this. Okay, so I'll tell you how to use this particular number line. So 20 is 2. Okay, that is fine, but the problem arises when we are dealing with letters, right? So it is a bit tricky. So what we do is, so we find for a, so we assign a value to this letter, right? So after 9, A is actually 10, B is 11, C is 12, D is 13, E is 14, F is 15. Okay, so here we have to add C plus 1. So if it is addition, we need to move to the right. Okay, had it been subtraction, we would have moved to the left. Okay, so it is C plus 1, so I'll move one step to the right, that is D. Okay, now how to perform the addition in this case? F. So F is actually, we will stand here and we have to move F positions to the right. Okay, F positions to the right means the value of F is 15, so 15 positions to the right. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so the 15th position is E. Okay, and because I did a turn once, so I will have 1 as a carry to the next number. Okay, so after getting a carry 1, so what will happen is, let us stand at E here. Okay, and now we have to move E plus 1 steps towards the right. So E plus 1 means 14 plus 1, that is 15 steps towards the right. Okay, so we are going to get a turn, so we will have 1 in carry. Okay, and the output will be D, because if you again count till 15 steps from E, so it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you will arrive at D, and similarly you can do for the rest of the parts. Okay, so this number line system is actually handy, that will help you to arrive at the correct answer. So you can use it, and once you are having a good practice with this number system, so you will find it easy to do without using the number line. Okay, so those were the important questions from week 1. So moving to week 2, so week 2 was mostly floating point representation. So this is the basics part. Let us jump to the numerical. Okay, so we were supposed to represent 23 in single precision floating point. Single precision floating point representation. So the first bit is actually the sign bit. Okay, because 23 is a positive number, the sign is 0. Okay, so the next rest of the bits, okay, let us review here. So the next rest of the bits is exponent and significant. Okay, in IEEE single precision floating point representation, so 8 bits are exponent, okay, and 23 bits are significant. Okay, so when I say exponent, it is actually biased exponent. So what is biased exponent? It means whatever exponent we obtain, we add plus 127 to it to obtain the biased exponent. So 127 is the bias value. Okay, so let us first represent 23. Okay, so 23 is, so we do the long division method, we obtain 23 as 10111. Okay, and we have to write it in this particular format because we have to standardize everything as per the IEEE floating point binary representation. So I write it in this format, 1.0111 into 2 power 4. Okay, so here the exponent is 4, right? To make it bias exponent, what I do is I add plus 127 to it. Okay, and here I just represent their binary equivalent. So 4 is 00100 and 127 is this particular number. and after performing the addition, whatever value we obtain, that is the biased exponent that goes here. Okay, remaining rest of the bits from 0, 1, 1, 1 till everything 0. So you have to append it in such a way, append the zeros in such a way that total number of bits in this field, the significant field, is 23. Okay, so after doing that, we obtain option number A as our answer. Okay, similarly, the next question was related to representation of minus 0.75 in IEEE single precision format. So first thing that we will do is we will convert 0.75 to binary. So 0.75, I can write it as 0.5 plus 0.25, right? And I know 0.5 is 1 by 2 or 0.1. For 0.25, I can write it as 0.01, right? So basically it is 0.11 in binary representation, right? And for IEEE standard format, I have to keep it in 1.xyz format, right? So to get it in 1.xyz format, what I do is I write it as 1.1 into 2 power minus 1. Okay, so here 1 is implied anyways. Implied means you need not represent it in the significant field. Okay, so my exponent is minus 1. To get biased exponent, what I do is minus 1 plus 127. Okay, then we will get 126, and I just convert that into binary. That goes directly into this field. And for my significant, what I do is whatever value is remaining here, so what is remaining is 1 and all zeros. Okay, and because it was negative, so my sign is 1. So option A was correct. Okay, similarly, so we are given the single precision floating point number representation, and we have to figure out its decimal equivalent. Okay, so we will see the sign bit first. It is 1. It means the number is going to be negative. Okay, next we pick the 8 bits. That is going to be our biased exponent. Okay, so 8 bits, this translates to 129. And from biased exponent, how to get the unbiased exponent? Because to get the biased exponent, we added plus 127. So to get the unbiased exponent, we are going to subtract 127. Okay, so here also we subtract 127 from this biased exponent and we obtain 2. Okay, rest the significant field is 0, 1, 0, and rest everything is 0, right? So I will write dot 0, 1, 0 here, and because in this representation I know that there has to be an implied 1, so I add a 1 here, and 2 into 2 to the power 2. Okay, 2 to the power 2 means decimal point will move to the right by 2 places. So my final answer should be minus 101, that is minus 5. Okay, so the next question is related to product of max terms representation. So a Boolean function, it can be represented in 2 ways, min term and max term. Min term and max term. So in this particular question, we were supposed to represent it in, we have to represent the max terms, right? So what I do is, first I make a Carnot map. From that Carnot map, using A, B, D as the variable, so I mark out the regions for which this f is equal to 1. Okay, so after marking out the regions for which f is equal to 1, the other regions are going to be 0. Okay, so you just take the product of other regions which are 0. So here it is 0 to 6, 4. Yeah, here it is written 0 to 6, 4. Okay, that is going to be your answer. Okay, and whenever a representation is given like this, okay, where one of the variable is not present, you have to understand that this is actually a b bar d plus a bar b bar d. and accordingly you have to fill the Carnot. Okay. Yeah. So the next question uses simple floating point model, and we have to find out 12 and 1.25 sum. Okay. So the first thing that I do is I convert 12 into binary. I also convert 1.25 into binary. Okay. Then after converting into binary, I represent it in the standard format. Okay. And remember, in standard format for simple floating point, there is no implied one. So you have to take 0.xyz. Okay. So we get 1100. I represent it in standard format. That becomes 0.11 into 2 power 4. Okay. So now we need to add the bias. So the bias addition for this simple floating point is you have to add plus 16 as the bias. Okay, so 4 plus 16 is 20, and then I represent it in this form. Okay, so parallelly I will do the same thing with 1.25 as well, but when I do with 1.25, if I represent it in the standard form, it will be into 2 power 1. But we need to ensure that the exponents are same. Okay, so what I will do is I will multiply 2 power 3 and I will divide 2 power 3. So if I multiply 2 power 3, 2 power 1 becomes 2 power 4. If I divide 2 power minus 3, if I divide 2 power 3, then the decimal place is going to shift to the left by 3 units, right? Okay, and then I do the same thing here. So the exponent is 4, the bias exponent will be 4 plus 16, that is 20. Okay, so this is 20. So after getting the final representation in both the cases, I just need to perform addition of the significants. Okay, and whatever is the result, you just mention the final result in the significant field. The exponent is going to be same, the sign will remain the same. Okay, so the next question is related to IEEE single precision floating point format, and so we did a similar question before as well. So the first bit you figure out whether it is 1 or 0. If it is 1, it is a negative number. Next you take the 8 bits. So the 8 bits actually represent your biased exponent form. You convert the biased one into unbiased one by subtracting minus 127. Okay, then rest of the bits will form your significant. Okay, so here we obtain minus 26 by this process as the answer. Okay, so moving on to week 3. So in week 3 what we did is we were supposed to figure out which of the following is not a prime implicant of the given function. So the function is given like this. Okay, so what is a prime implicant? So prime implicant is it's a product term that is obtained by combining the maximum possible number of adjacent squares. Like if any term is present, so last time I gave this example, so let's say a1 is present here, 1 is present here and here. So if you choose this one and you have to figure out the prime implicant, you need to see how many adjacent ones are there and have you clubbed all those ones. If you have clubbed all the ones that are present adjacent to that one, then it will form a prime implicant. Okay, so in this case you can see that this one and this one can be clubbed together, right? So that forms a prime implicant, right? And if a minterm in a square is covered by only one prime implicant, then that prime implicant is said to be essential. Okay, so that is about essential and essential prime implicant and prime implicant. So what we do is we try to first figure out what are the missing terms. So we see D is missing here, D is missing here, here, and here C is missing. So to get the missing terms, we use this property. Okay, If we multiply the missing terms with their complement in each of the terms, then we will be able to get back the missing terms. Then I write it in the form of sum of min terms. Okay, then I arrange it in Carnot map. Okay, after arranging it in Carnot map, I see which ones can be clubbed together to form the prime implicant. Okay, so similarly I see that there are 4 ones present here, so they should be clubbed together to form a prime implicant. Okay, similarly I see 2 ones are present here, 1 is present here, so I club these 2 in one group, then I club this one and this one in one group. Okay, so I list all the prime implicants that are present, and I see which prime implicant is essential. Okay. And accordingly I solved this question. Okay, moving on to the next week's lecture. Yeah, so in this week, in week 5, so one important question was related to BCD addition. So in BCD addition, what you need to do is, so you have 9, 6. Okay, so you represent 9 as a binary, and you represent 6 as a binary here. The same thing you do with the other number. Okay, after doing that, you perform simple addition. So after performing simple addition, this was the result. Okay, but whatever result is obtained is not in BCD. You need to get the answer in BCD. So to get the answer in BCD, you individually add the bits with +6. Okay, so the reason for doing this is so the BCD digits actually end at 9, right? So when you move from, okay, let me call this digit 2 of BCD, digit 1 of BCD. So earlier it was 0, 9. Please tell me the example of prime implicant. Okay, so in this, hello,
sir.
Yeah,
Sir, good afternoon, sir.
Good afternoon.
Can you explain that one, how we are going to use the prime implicants and essential prime implicants?
Okay.
The difference between those two.
Okay, so prime implicant means which is like, let's say there is a 1 present, okay, at any place. Okay, so if that one can be clubbed with another one that is present adjacent to it, okay, and you go on clubbing all those ones together. Okay, so if you have covered all the ones together, then that particular implicant will be called as a prime implicant. Okay, so let me give an example here. So can you see this quad?
Yes, sir.
Can you see this thing that I marked in blue?
Yes.
Okay.
I am seeing.
So let us say 1, 1, 1, 1 is present here. Okay. So if I take only one of them, okay, so can I call it an implicant?
Yes.
Yeah, it is an implicant. But is this particular one a prime implicant?
No.
No. The reason is because there are ones adjacent to it and I haven't clubbed them. So if you see a 1, so you ask a question, can I club them with any other one? Okay, so if the answer is yes, if you can club them with any other one, then that particular number is not a prime implicant. You need to get it clubbed first. So club as much as possible till you reach the limit of clubbing. Okay, and once you have reached the maximum number of ones that can be clubbed together, whatever implicant you arrive at, that is your prime implicant.
Okay.
Okay.
Okay, sir.
Yeah.
But how can we say the difference between that essential prime implicants and the simple prime implicants?
Okay, So if let us say one prime implicant is covered by only okay, so take this example of this particular quad. Okay, so
Okay.
if you don't present this quad, so can all the implicants present here be represented by any other term, like any other prime implicant?
No.
Right. So because this one is not being covered by any other prime implicant, this one is not being covered by any other prime implicant, so it is essential to use this implicant, right?
Okay.
So in that case it becomes a essential prime implicant.
Okay.
So is that clear?
Okay. That is essential prime implicant.
Yes.
Whereas prime implicant means we are going to join that same variable with other number also.
Correct.
Okay.
Okay.
Okay, sir.
Okay. So yeah. So okay. So I was giving the reason why we need to add +6. So just a minute. Okay. So let us say that yeah, in BCD 09 is possible, and if we want to move from 09 to 10, okay, so 09 will be 0000 and 1001, and this will be 1 and all zeros, right? So if you talk in terms of decimal, in terms of binary, this is 9 and this is, can anyone tell me how much is this? Yeah, this is basically 16, right? So to get from 9 to 10, okay, so I have to travel a distance of 7 units. So had it been 10, okay, so I need to represent 10 like this, 1010. So the correct amount between them is 10 minus 6, sorry, 16 minus 10, that is +6. Okay, so 16 is the equivalent representation in BCD, and 1010 is the actual representation in binary, and the error between these two is actually 6. Okay, and because of this reason I need to add +6 to the binary values to get to the BCD number. Is that clear?
Yeah.
Okay, so the next question is related to, so we have two functions given, okay, so a and b, and we have to figure out what does this function implement. Okay, so whenever a question like this is given, so first thing that we do is we draw the truth table. Okay, you represent all the inputs present here and whatever are the corresponding outputs. Okay, then accordingly, so you start giving 000, 001, 010, each and everything in the input, and you observe what is a and b. Okay, so after observing what is a and b, what we see is whenever I1 is 1, okay, so AB value is 01. Whenever I2 is 1, irrespective of whatever I1 value is, AB is 10. Similarly, whenever I3 is 1, irrespective of I2, I1 value, AB is 11. Okay, so this is actually the behavior of a priority encoder. Based on the higher bit, the value of AB is decided. Okay, so using this truth table method, you can figure out what is the behavior of a circuit. Okay, then moving to the week 6 content. So in week 6, so one of the important question was this one. So if two up counters are cascaded together, then what will be the resultant counter? So a simple formula is, if you have to figure out what is mod X, okay, if you have two mod A mod B counters and you just cascade them together, mod X will be equal to mod A into B. Okay, so that is the formula that you can use to quickly solve your questions. For logical explanation, what you do is you take a clock, okay, and mod 2 means, so it will have two states, 0 and 1, right? Means after each second clock edge, second clock edge, it is going to trigger to either 1 level or 0 level. So we do the same thing based on the clock pulse. So here 1, here 2, okay. So after 2 clock pulses, it is going to get down, and similarly it is going to repeat and so on. Okay, now for mod 5 you need to count 5 clock pulses, right? So I calculate 0, 1, 2, 3, 4. Okay, so total 5 clock pulses. After that it goes to 0. Okay, so now if you check for 5 clock pulses how much time it took in terms of your actual clock pulses from the CLK, it is actually going to be 10 clocks, right? So 10 clocks implies that it is behaving as mod 10 counter. Okay. So, or else you can simply remember this formula, that will be handy for calculating. Okay, so the next question was related to sequential circuits. You are given a sequence 0 0 1 1 0 1 1 0. You have to figure out what is the combination of DA and DB to obtain this particular sequence. Okay, so so when the present state is 0 0, so pay attention here. So when the present state is 0 0, next state becomes 1 1. So what should be the value of DB and DA? So it should be equal to the next state, right? So that's what I did. So whatever is QB plus, I wrote it in DB and DA. And once it is 1 1, then what happens? It goes to 0 1, right? So in the next stage my present state becomes 1 1, my next state becomes 0 1, and DB DA is equal to the next state. Okay, similarly I go on doing this till I reach all the combinations. Okay, then I need to figure out what is the equation for DB, what is the equation for DA. Okay, so I just observe what is the location of QB and QA for which DB is 1. Okay, so I just mark these locations as 0 0 0, 1 1 as 3, 0 1 as 1, 1 0 as 2. Okay, then I write DB as summation of min terms 0 and 1. Okay, same thing I do with DA. I write it as summation of min terms 0 and 3. So finally I obtain DA is equal to QA bar QB bar plus QA QB and DB as QB bar. Okay. Yeah, the next question is related to the terminal value. So using 2 to the power n minus 1, this formula, you can arrive at the terminal value. So 4-bit counter means 2 to the power 4 minus 1, that is 16 minus 1, that is 15. Okay. So moving to week 7's content. So in this particular question, we were supposed to figure out the output sequence, given that the initial sequence is 0 0. So the first step that we do is figure out the equation for JA, KA and JB, KB. So JA is the J and K value of flip-flop A, JB, KB is the J and K value that is being fed to flip-flop B. So for figuring out JA and KA, you just see whatever is connected to these gates and how are JA being excited. Okay, after obtaining the values, use the information that is available with you, that is AB initially is given as 0 0. So when AB is 0 0 initially, okay, then you look at the timing diagram to note the value of X. For the first clock, the X value is 0. So when X is 0, using this equation, JB is 1, KB is 0 because A is 0, X is 0, KA is 0 because B is 0, because initially A and B are given as both 0 0, and JA is 0. So we have JAKA 0 0. Okay, so if JAKA is 0 0, so the value of A is going to remain same. So the value of A is 0, A plus is also 0. But what about B? So what happens? JB is 1, KB is equal to 0. So it means the next state value of B will be 1 irrespective of whatever was the present state. So that is what happens. So the next value is 0 1. Similarly, you go on evaluating for the rest of the cases, observing the timing diagram, and you will obtain it as 1 0. Okay. So please pay attention to the clock edges. Okay. First, take a note of whether this is positive edge or negative edge. If there is a bubble or if there is a bar over the clock, then it is a negative edge clock. If there is no bubble or no bar, then it's a positive edge clock. And accordingly, sample those values of X like we did in this case. We marked the positive edge, we sampled those particular values, and accordingly we solved the questions. So any set of tricky questions can also be asked. So please pay attention to the clock edges, which is triggering the flip-flops. Okay. So the next question was related to, so you have a given state table of a sequential circuit, and the initial state of the circuit is given as 0 0, and you have to figure out what is the output for given sequence of X. So where X is the input. Okay. So you start with 0 0 as the state, initial state, then first input is mentioned as 1. So if X is 1, so from this state table you figure out that this is your required row, so the output is 0. Okay. Similarly, the state changes to 0 1 if the input is assigned as 1. So 0 1 1. So 0 1 1 means this is the next state, and in this state also the output is 0. Okay. Similarly, you see what is the next state, that is 1 0, and for 1 0 what is the corresponding input, that is 1. Okay. So 1 0 1 is the next state and the output is again 0. Okay. And in this case the next state is 1 1 and the input is 0. So 1 1 0 is the next state and the output is 1 in this case, and so on you repeat for the last one as well. Okay. Okay. So the next question deals with figuring out the mod value of the asynchronous counter. So whenever you see a reset, so first thing that you should check is whether that reset is active high or active low. Okay. So as I mentioned that if we see a bubble or a bar, then it is active low. So in this case the reset is active low. It means that whenever the reset is 0, then it gets reset. The next thing that we do is we try to figure out the equation for the reset. Okay. So to figure out the equation for the reset, we see that it is a NAND gate and the input to the NAND gate is coming from QA and QD. Okay, let's ignore the clock for the time being. So this line is for the clock. Okay. So and QA dot QD bar is going to set your reset to low when QA equals to QD equals to 1. Right? But we can have more than one options. Right? So QA QD is 1 1, but QC QB can obtain any value. Okay. for getting the reset. But we will take note of the first value that arrives when going from 0 to there are 4 flip-flops, so 0 to 15. Right? So when going from 0 to 15, what is the minimum value that is going to set your QD and QA? Okay, that is going to be 9. Okay, so our terminal state is going to be 9, 1001. And once it reaches 9, everything is reset and it goes back to 0. So the total number of state is from 0 to 9. That is 10 states. So the mod of this counter is 10. Okay, moving to the week 8's portion. So week 8's portion, so this question is related to a flash ADC. Okay, so the basic operation of this comparator is, so whenever you apply an input Vx greater than Vy, then it will go to the positive saturation. So positive saturation is the VDD. Okay, and in digital logic we call it 1. Had it been analog, we would have called it VDD, but in digital it is 1. Okay, and if Vy greater than Vx, then we are going to have output as 0. Okay, so that using that basic logic of the comparators, first thing that you need to do is figure out what is the comparator voltages. Okay, you have Vref given to you. Okay, you know the number of resistors that are present here. Okay, so you find out the comparator node voltages. Okay, so the comparator node voltages will be, so here we are taking the voltage across only one resistor, so it will be R by 8R into Vref, that is 1 by 8 into Vref is 16, that is equals to 2 volt. Similarly here it is across 2 resistors, so it will be 4 volt. 3 resistors 6 volt, so on 8 volt, 10 volt, 12 volt, 14 volt. Okay, then you figure out what is the V input. Okay, and whatever V input you have obtained, you see for what value the comparator is going to give you a 1. Okay, so we see in the first case, so V input is actually connected to the positive terminal. It means unless this V input is greater than the reference value, it is not going to turn on. Okay, so in the first case the reference was 14 volt and this is 10.13, it was less, so it is 0. Next case it was 12 volt, 12 is again greater than V input, so it is 0. But in the next case it is being compared with 10 and it is greater than 10, so it is 1. If one of the bits is greater than 10, it means if one of the value is greater than the reference value, it means the rest of the value will also be greater than the reference value. So rest of the bits will also be 1. Okay, then you arrange them in this format. Okay, starting from D7, which is denoted here, to D0. Okay, then you see which of the maximum bit is high. In this case D5 was high. Okay, so the equivalent should be 5. The encoder's output should be 5. 5 in binary is 101. Moving to week 9's content. So in week 9's content, the important problem that was present is related to Hamming code. Okay, and so in this question we are given a binary code 1111, means total 8 ones, and we need to figure out what is the even parity Hamming code. Okay, so the first thing that we need to do is we need to figure out how many bits we need to add. So there is a formula called 2 to the power k minus 1 greater than n plus k, where n is the number of data bits. So in our case it was 8. Okay, plus k is the number of bits that needs to be added, right? So we obtain an equation 2 power k greater than equal to 9 plus k. And what is the minimum value of k that satisfies this equation? That is k equals to 4, right? Because if we take k equals to 3, we have 8 on the left side and we already have 9 on the right side, so that equation is going to be wrong. So k is equal to 4 is the least value of k for which it is satisfied, so it means we will add 4 bits. But 4 bits cannot be added arbitrarily, so it has to be added in 2 to the power nth location. It means you can add it in 2 power 0th location, 2 power 1, 2 power 2, 2 power 3 location. So you just write a position vector mentioning 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and you take all the you first fill the position where the parity bits will be present. So here the parity bits will be present in 1, 2, 4 and 8 position, so that's why I filled them first. Then you add the data bits. Okay, after adding that, your role is to figure out what is P1, P2, P4, P8 and replace them here. So for P1, the logic is starting from the P1's location, you pick 1 bit, you skip 1 bit, you pick 1 bit, you skip 1 bit. So it will be 1, then 2 is missing, 3, then 4 is missing, 5, 6 is missing, 7, 8 is missing, 9, 10 is missing, 11. And you take the XOR of those bits. And because even parity is asked, so if I take the XOR of those bits, that should be 0. Okay, using those equations, I'll figure out what is P1. Similarly, for P2, starting from position 2, I'll pick 2 bits, I'll drop 2 bits. So 2, 3 picked, 4, 5 dropped, 6, 7 picked, 8, 9 dropped, 10, 11 picked. Okay, then you again do the same thing. Similarly for P4, you start with position 4, you pick 4 bits, you drop 4 bits, then you again pick 4 bits, means the last one is 12. So okay, similarly for P8 you repeat the same thing, and at the end you will arrive at your desired parity bits value and just replace them here. Okay, and that will be your answer. Okay, so the next thing was to identify the error in the location. Identify the location of the error in the received stream. Okay, so whatever was the received stream, so at the position of the parity bits, we add these set of bits which let us assign them a letter C. Okay, so you just take the parity bits location, whatever is present. Okay, and to figure out what is C1, C2, C4 and C8, what you need to do is similarly whatever you did for finding out P1, right, do the same thing for C1. You pick 1, you drop 1. For C2 you pick 2, you drop 2 and take the XOR of that. Okay, and whatever value you obtain, arrange them in this format: C8 first and C1 last. If the complete value is 0, it means there is no error in transmission. If the value is non-zero, then the non-zero value that is obtained, in this case it is 7, it means that the 7th bit is erroneous. Okay, moving on to week 11. Okay, so in week 11 one important problem was related to figuring out the content of the accumulator. So we are given a set of instructions, and so MVI A will move 65H into accumulator, MVI B will move 12H into B, and then add B will add 12H to 65H, and the accumulator value becomes 77H. Okay, so 77H is 0, 111, 0, 111. Then after the CMA instruction, so it becomes 1000, 1000. Okay, then after the last instruction ANI 68H, So what happens is we take 6 8 and we perform AND with that, we obtain 08H, okay, as the answer. Okay, so the next question is related to computing the total delay that is produced by this given program. Okay, so to figure out the delay in such a case, we need to figure out what is the delay outside the loop and what is the delay inside the loop. So figuring out the delay outside the loop is easy. Just see whatever is present outside the loop. In this case it is only 10t, so I present 10t. Delay inside the loop, so you are given the individual delay of all the instructions, but there is a catch here in the JNZ instruction. So JNZ instruction, each time it is executing the instruction, it is 10t, but for the last iteration it is 70. Okay, so then you see how many times this instruction is being executed. So that depends on your B, the content of B register. So the content of BC register is 0123, that stands for 291. So it means this loop will be executed for 291 times, right? So 291 times the delay of the internal loop is the total delay inside the loop. Okay, so 291 into 6 plus 4 plus 4 plus 10. But as I mentioned that the last JNZ statement needs only 70 states. So what I do is I subtract minus 3 here. Okay, then we obtain total number of T states as 6981 T states as the total number of T states for inside the loop. Okay, then for outside the loop we have 10T as the T states. So the total T states needed is 6991 T states. Then we have the information, if we want to convert from T states to absolute delay in terms of millisecond or microsecond, we have this information that it is operated at 5 megahertz. Okay, so if it is operated at 5 megahertz, then it means the time period is 1 by 5 microsecond. So 1 by 5 microsecond is actually 1 T state. So 6991 T state will imply 6991 into 1 by 5 microsecond. Then we obtain 1.398 millisecond as the answer. Then from week 12, one important problem was related to setting the sim instruction, right? So for sim instruction, set interrupt mask, what we need to see is whatever is the content of A. In this case the content of A was 2AH. Okay, and please remember, so the positions for setting the interrupt masks, that is given on the right hand side. So the first bit, it corresponds to serial data output, second bit is the enable serial data, third bit is not used, fourth bit is RST 7.5, it will reset the RST 7.5. Then next bit was mask set enable. If it is 0, then it will ignore the rest of the bits to the right. If it is 1, then it will set the mask according to bit 0 to 2. Okay, so in our case 0010, so 0010, okay, it means nothing from this side. Okay, then 1010, so 1010 means you set MSE as 1, M7.5 as 0, M6.5 as 1, M5.5 as 0. So it means the RST 6.5 interrupt is going to be masked, but others are 0, so others won't be masked. So option B is correct. Okay, yeah, so that was all about the important numericals that I thought we should revisit. And yeah, so there were also other questions that were not that were similar to these questions, and there were some one or two tutorial questions that I covered, that was some additional problem. So I'll suggest you to go through the lecture video, you can go through the lecture videos and the live session videos. So those are already available on the YouTube channel. So if you still feel that there can be any other important problems that I did not cover it in this session, so it is already covered in the previous sessions. You can go through them, and I try to touch upon most of the important problems that we have done, and rest of the problems are just mild variations from these set of problems. So I don't think you will face any issues there. But if you face any issues, just let me know either through the forum, through the forum, so that will be better. I can address it there. You can go through the recorded lectures, you can go through the slides that are shared with you. Okay, so so if anyone has any queries or any questions, they can let me know. Does anyone have any questions? Hello. Okay. Okay, then if anyone has any question, then let me know. Otherwise, all the best for your exams. So I hope these sessions were helpful. SIM in MPMC. Okay, so is this particular slide visible where SIM instruction is mentioned?
Yes, sir.
Okay.
Regarding that values, for example, they instead of giving that A or 2A, for example, if they have given the value 3A,
okay,
at that time, how can you find out that operation?
Okay, so for 3A, we will have 0, 0, 1, 1, and A is 1, 0, 1, 0. Right? So,
yes,
correspondingly, you can place the bits here 0, 0, 1, 1. Okay, and rest is 1, 0, 1, 0. Fine. So it means, so if it is 0, then we don't need to bother about these two. And this bit is unused. So let us look at the last bit, that is 1. It means that RST 7.5, it is going to reset. Okay. And the rest of the bits will have the same meaning as in our previous examples. Okay, so it means 1010 will mean that mask set enable is 1 and M6.5 is going to be 1. It means M6.5 will be masked, but the RST 7.5 is going to be reset. Okay.
Means at that time they will give the option that is reset 7.5 is enabled, or it is going to replace that value. In addition to that, the value of that 6.5 is masked.
Yes, correct. Okay, so similarly, you can take another example. Let us say here it would have been instead of 2A, let us say 2F. Okay. So what would have happened is this is 0 0 1 0, okay, and then rest all are 1. Okay, rest all are 1
Yes.
means all of these would have been masked. Got it?
Okay.
So if this bit, if any of the last 3 bit is 1, then it means that it is going to be masked. So I have written it here. So if it is 1, it is masked. If it is 0, it is unmasked.
Yes.
Okay. So similarly for this bit, if it is 0, then ignore bit 7. If it is 1, then send bit 7 to SOD. Okay.
Okay.
So yeah, so these are the interpretations. So it is also mentioned in an elaborative way in the lecture slides as well. So maybe you can visit them if you want. Okay. So that was about SIM's operation. Yeah. Is there any other query? Okay, so if there are no more queries, then yeah, so this was the last session that I'll be taking. So probably tomorrow there is another session by another TA. But yeah, I thank you all for joining, and all the best for your exams. So yeah, you can go through the recorded lectures that is available, and if you have any query, then please let me know. Okay. Yep. Thanks for joining, everyone. Yeah, Suresh, you had any question? Okay. Yeah, actually today's session we have already completed, and so in today's session what I did is I discussed some important problems, so roughly 30 or 32 problems. So this was brief recap from the previous weeks. Yeah, so and we discussed one or two doubts, so I don't. Yeah, sure, okay. I'll upload the recording after 5:30. It will be available on the channel. Okay. Yeah, and all the best for your exams. Oh, okay, sure, no problem. Yes. Sorry, you asked fixed point representation. Not sure. Was fixed point representation covered in your course? No, then you don't need. Means for exam point of view, if it is not covered in the course, then no. But if you want to learn fixed point representation, then yeah, it's a good thing to learn, right? When you actually want to design a hardware or something.
Actually, when I was in graduation, right, that time period, we had this fixed point also.
Okay.
So just want to ask that whether we are going to get those questions or not. In the presentations, I didn't see related to that. Actually, looks like week 1 and week 2 are fine. Maybe from week number 6 onwards. I think looks like these numbers are. I mean, these are very basic questions. I feel.
Yeah. Yeah.
Okay.
So week 6, I found this one means these questions important. So I discussed it again, and whatever rest of the questions also we did in week 6, it was more or less a variation of these questions, right? So if you cover one, then others can be. Same thing with this one. Then week 7, okay, this one was there.
Okay. Yeah.
Then figuring out the sequence output.
Yeah. I tried many problems for them. Actually. So for example, mod counter, right? Do we have anything like number of flip-flops required in order to get mod 10, mod 5, the formula?
Yes, you can figure that out. No? Means let's say if it is how many? Okay, you give me a number.
Let's say it is a mod 10 counter. Let's say how many minimum number of flip-flops are required?
Yeah, that is
a question related to that.
Yeah, that is 4 now. Because see, so you think in terms of this. So you tell me any number, let's say 13, 14 or anything. So to represent the number 13, how many bits will you need?
Minimum 4 bits are required.
Correct. So minimum 4 bits implies minimum 4 flip-flops.
Okay, alright.
Okay.
So it is like 2 power L. Yeah.
Exactly. So if you use log base 2 and
Okay. The question is related to this. I mean, sometimes we have ring counters, sometimes we have Johnson ring counters, right?
Yeah.
So in that case, do we have any difference between them in order to find out in the two special cases?
I think that will be also related to the final terminal count. Okay, so let's say in Johnson counter, if the terminal count is, let's say, 16.
Yes. Okay.
So for representing 16, you will need 5 bits. Right, because 1 and then 4 zeros.
But in between, we don't have all the patterns. That is what I'm thinking.
Agree.
So sometimes.
But all those patterns are not there. But to represent that particular number, you will need that many flip-flops.
Okay, understood. Okay.
Yeah.
Okay, got it. So irrespective of the number of patterns that are appearing in the ring counter, doesn't matter. But in order to represent that, we may need to have the 2 power N mod.
Correct. Correct.
Okay.
So from the terminal state, you can figure out the number of flip-flops.
Okay.
Then, week 7 was mostly factual. Week 7 we covered. Week 8 was this one. So this one we did 3 or 4 questions similar to this. So I just covered one of them. And here the basic logic was to figure out what is the reference node voltages here. And then solve it. Right?
Okay. Yeah, correct.
Yeah. So week 9, the Hamming code part, that was part of the problem, right? So week 9 we did 2 examples. One was related to figuring out the parity bits, and another question was related to figuring out the error location in the stream.
Okay, if we get this C1, C2, C3, C4, then we will come to know that which error it is.
Correct.
Yeah.
So this was about, and week 10 was mostly, I think, semiconductor memories, right? So memories part was mostly, it was factual. So so a lot of theory stuff. In week 11 was 8085 content of accumulator. So content of accumulator, it depends what kind of question appears, and based on that you need to solve. So we just took one question. Then the next thing that I thought is important is related to that delay calculation.
Yes.
Okay, so
And what about this? It is having two answers, right? Here, A and C.
A and C, is C correct? Wait, let me check. Let's say this is 1.398 into 10 power minus 3. This is 1398 into 10 power minus 6. No, right?
I think if we go by the process, right, then we will get the answer C instead of A. I mean, 1.398 milliseconds is nothing but 1398 microseconds. Only 0.2 microseconds variation will be there.
Yeah.
So that's what I'm thinking. So here it will be like BC register count will be decreased by 1, right? So inside and outside we will get 291. And actually I have discussed this with one of the teaching assistants in other classes, I think. So when he was explaining, I think he is Sachin or somebody else. I mailed him regarding that.
Okay.
And we agree upon okay, week 11, right? It is week 11 question number
week
8.
11 question number
Okay. And last instruction is 291 is the total number of count into 24. And minus 3 is for the last one is
JNZ.
minus 3, right?
Yeah. Because we had to do it 70.
6.
Yeah.
Yes, correct. So 291 into 24 minus 3. So it is 6981. That's what I have also got, 6981. If I multiply that with 0.2, then we'll get
but why
6981 plus. No, I think T states, right? In order to get the T state, so I'm considering the T.
Yeah. Actually, I did it. I did this calculation. I got this one exactly 1.398 millisecond. I didn't get the 0.2 thing.
Oh, is it?
Yeah. Let me get my calculator.
6991 into 0.2.
Correct. Yeah, it is. Wait. Okay. Yeah, actually there will be 0.2. There will be 2.
Okay, anyway, but these two are very close by.
Yeah.
But if we want to have more accurate, then C would be the correct answer instead of A.
Yeah, A and C both should be the answer.
Actually, when I was trying with this elimination method, right, at that time I found that 0.2 will not be the case. So D is eliminated. This is because of one T state, right? One T state it is.
Yeah.
So since I am seeing many T states, so option D is eliminated. After that, I went for 1.398. 1.398 is only 5 or 6 T states.
Correct.
1.2. So B is also eliminated, BD eliminated, and I don't think so it will be in the order of milliseconds. So I got the answer C.
Okay.
I mean, elimination method I was able to. But later I found that 1.3982 milliseconds, maybe, because here the precision important. If the precision is very important, then C is the correct answer.
Yeah. Actually, both A and C should be correct because I don't see any reason for dropping C or dropping A. Yeah. Both A and C should be correct.
If it is round up to single decimal point, also both will be correct. Actually.
Yeah.
Only point. Okay. Yeah, we'll go by next. Actually, I thought I've been attending to all the TA sessions, so I'm catching different problems actually.
Oh, okay.
All 4 actually, Sachin, you and some other person. Have you been ever TA for the course earlier?
No.
Not. Okay. Just want to understand that what the question paper pattern, how it is going to be set. Okay.
I'm not sure. So this is the first time I am TA for an NPTEL course.
Oh, okay, I see. Somebody in the same TA, he was earlier TA for this course actually, digital circuits.
Okay.
I think might be he's a PhD scholar for a long time. I think maybe 3 years or 4 years. I don't know. Maybe. Okay. Yeah, question number 8 is clear. Okay. All
Yeah.
right.
Then after this, we did only one question from week 12. This was
Okay.
this
This is
question.
also clear. Yeah.
Yeah. So that was all the important ones that I think. Rest were like minor variations
Okay.
only, not something big.
Yes. Yes. Okay.
Yeah.
This is register. Remembering is
Correct.
register. Remembering the register flags. Okay.
Yeah. So once you remember the register, any kind of problem related to sim, or there was another one, right? Flags.
Yes. Yes.
Yeah. So those things will be resolved.
Okay. Week 12 is only one. Week 11 is already covered. Week 10 it is theoretical.
Yeah.
Memories.
Week 10
Okay.
was completely theoretical.
Yeah. Okay. I have been through the previous years.
Okay. Hello. Suresh, I think.
Right to you.
Hello. Suresh.
Yeah.
Can
Can you hear me?
Yes, I can hear now.
Can you hear me?
Yes, I can hear.
Okay. I have been solving. I've been solving the previous year assignment questions. I had some queries. If you can provide your email address, right? I can write to you.
Email address, I don't think so. See, the NPTEL team asked us to address the queries on the forum itself. So otherwise, what you can do is maybe in the if you can put it
Forum
in
I can
YouTube,
ask.
YouTube chat box also you can ask. I guess I don't know. Forum is preferable because the team like they want to keep track of whatever queries are asked and those things.
Okay, no problem. I'll ask that then.
Yeah.
So most of the questions are covered actually.
Yeah.
So only few items I may be having, but the question might be also sometimes wrong, right? They may be framing the questions in the wrong way.
Yes, that is also possible.
So maybe I'll see that and then accordingly I can ask. And one more thing is this ADC part, right? Where we have the full string. So we need to consider the 2 port n minus 1 steps only, right? In order to determine the step size. Okay.
Correct.
But the minor variation is related instead of 2 power n.
Yeah. See, what we do is like in practical, like real life design cases, right? So let's say n is 10. Okay. So it doesn't matter whether it is 1024 or 1023. So that approximation we can keep. But if let's say n is very less, like around 2 or 4, right? So it is going to matter whether you are considering the -1 or not. So it's better to keep -1 in mind.
Some question related to this has been asked in the last previous assignment, which is very small number. I think it is having only 4-bit.
Okay.
The full scale of a 4-bit DAC produce output of 0.1 volt.
Okay.
For a digital input of 0001, that is the LSB minimum value. So the step size they are saying 0.1 volt.
Okay.
We need to find out full scale output how much it should be.
Okay.
Here in the options they have given 1.5, 1.6 also.
Oh, okay. Then if that degree of precision is needed,
Because other TAs, right? I've been to other TAs also. One of the TAs told us doesn't matter because if the pressure is very large, you will get the point decimal values change.
That is true.
Very short value.
Yes.
Very short value, then we need to reconsider that approach.
And in like for questions and exams, it makes sense whether you keep -1 and not. But as I said, like in practical cases, we never deal with such low resolution, right?
Yes,
So
yes, yes.
yeah,
Because we use minimum of 16-bit and
correct,
32-bit based in the
exactly.
applications.
Yeah, yeah.
Mm.
So yeah, that was it. And your exam is on 28th, is it?
Yes, yes, 28 next week.
Okay.
Exactly. By this time, we would be in the exam. I think
Oh,
we would have completed.
okay, okay, great.
Yeah.
Okay. All
Next
the
week,
best for
28.
exam.
Thank you very much.
Okay.
So somebody else also joined.
Yeah. I think I'll suggest them to look at the recorded lecture. So,
Okay.
Priyanshu, you can go through today's session. The recorded lecture will be available after 5:30. So, I'll upload it in my YouTube channel.
Okay.
Yeah.
Yeah, anyway, we have a link for that also, right? From the course also we can access this. Yeah, in the Excel sheet it will be get updated.
Then that's good, because last time someone asked me to that they were not able to find the YouTube page. I said okay, then I'll share it. They asked me to send the link again. So,
Okay, okay. I can see them actually. Your recordings, except one lecture.
huh.
I'm not sure about which lecture it is, but except one lecture, I'm able to see all the links for the YouTube.
Oh, okay, okay.
Maybe I can confirm that also. Oh, which one I am not able to see? Arpit Bal, right? Yeah.
I think all I made visible, but I don't know.
One is missing. I think maybe the recording issue or something. I don't.
Which one?
Yeah, I'll check that. I'll check that.
Yeah, yeah.
Just give me a second. Almost all the sessions. Thank you for your support throughout the course. It's been very long time.
No problem.
Yours are visible. All are visible. Till week 12. Yeah.
Okay.
Only Sachin's is having some problem, but he also updated that.
Okay.
Yeah, I think Musaib Rafiq, he was the TA earlier.
Oh, okay. Yeah, yeah, yeah. Musaib, yeah.
Sachin Sampath and Arpit Bal, you. I don't know about TA, it was discontinuous, like it is not continuous. Maybe first week is available, 5, 6, 7, 8, 9, 10 is available, 11, 12 are not available.
Okay, okay.
Okay, I can see your, even week 12 also updated.
Yeah, yeah. Week 12
Yes.
I uploaded. Like I usually upload it just half an hour after this thing. So it takes some time to
Okay.
upload based on the internet speed. And today the speed is a bit not good. So let's see.
No problem. No problem. Anyway, we'll go through that lesson, right? So if I'm able to solve the problem, then I can skip the problem.
Yeah, sure.
Sometimes we may take only 1 or 2 minutes to solve the problem.
Yeah,
right?
yeah, yeah. Because see, total number of problems that we have covered is roughly around. Means it is greater than 150. It should be roughly 180.
Yes.
But yeah, so you need not go through all of the problems. Just see if the variety of problems that you are solving is good enough, then that should be fine. And solve the examples that were covered in the classes too, like during the lectures.
Actually, I am planning to solve this our assignment problems this year, last year assignment problems,
Okay.
and all 4 TAs. The problem solving sessions I am trying to solve.
Okay.
Let's see if something else is also not required, then I can go. So my plan is to go over all these things and along with the tutorial material.
Okay, okay.
So that's what I'm planning for. I have already completed all the TA's problem solving sessions.
Okay.
Just I'm thinking this year and last year assignments till 7th week I have completed. We need to see 5 more weeks.
Okay, okay.
The only thing is, especially this sequential circuits, the track of these things, right? Those are time consuming. That's what I felt.
Yeah, yeah, yeah. Actually, those are a bit time consuming, but what I have seen is with, if you practice more and more, so
Yes, yes.
it becomes like there is a pattern that gets set into your mind. Okay, that if I see 001 and things like this, then this is
Yes.
going to happen. Yeah.
Yeah,
So initially when we were also doing, so we also faced the same issue. but with practice it was like normal, and yeah. So I think with practice.
Actually, I'm a working professional now.
Oh,
I'm
okay.
working professional. Yeah, just want to make sure brushing up all these things one more time because it's been already 10 years.
Oh,
I have completed my graduation.
okay.
So that's why I want to brush all these things up one more time, maybe. So in order to do that, that's why I'm catching all these things.
Okay, okay. Yeah, that's a good thing then.
Yeah. Marks are not important anyway for me.
Yeah.
Because if I don't put these things right, exam, specified patterns, I can't learn.
Yeah.
I can't put in more efforts. So that's why I'm doing this. Okay.
Okay.
Thank you for your support.
Yeah, no problem.
Through the session.
I hope you liked the sessions, and if you have any,
of course.
Yeah. If you want to give any feedback, you can also let me know. So if
how can we give the feedback for a specific TA?
Usually they float some feedback forms as well. So either there you can mention means about the overall course, tutorials, everything. So they ask for feedbacks. So
okay. I'm sure that there will be feedback, but it is not with respect to TA point of view. I need to see this. I already wrote some exams in before this also.
Okay.
Okay, but I did not get specifically for a problem solving on for particular TA.
Oh, okay.
So that way I didn't get big because problem solving or whatever the previous the papers which I have taken were. Only the teaching assistant and professor all together will be in on class. It is not like problem solving.
Okay.
Now, this session we have a problem. So let's see. If it is there, then definitely I can give all four. I mean, I haven't been through the four last candidate, last TA, but three of you like Sachin or you or Rafiq, all three are very good actually.
Okay. Thanks.
At that time, I'm unable to catch some point, right? Because of lack of resources or lack of understanding or something else, right? But I'm getting those concepts now.
Okay.
Just because of you guys.
Thanks. It's good to know that the sessions are helpful.
Yeah, really, it will be helpful. It's not exam point of view. Maybe in the industry also, we may need to look into some other domains. Actually, I am working in VLSI. It's a signal integrity.
Okay. High-speed interconnect side.
Yes, high-speed interconnects. Yeah. If you want to see something related to digital, then we need to understand the timings and related the circuitry side inside.
Yeah.
So for that purpose, I am doing all these things. I have done my masters in BITS Pilani, which is embedded systems, and we are currently working from last 10 years. I want to enhance my skill sets by going through the basics one more time.
Okay.
That's how it started.
Okay.
It's really good actually. It is like a addiction for me to learn all these things again and again. It became addiction.
So you are planning to take any course next sem as well?
Yes, of course. Definitely I will take.
Okay, great.
Previous semester I took CMOS VLSI design.
Okay, by
I took
Shanti sir, was it? I think.
No, Shanti no. It's Dev Gupta.
Okay, yeah.
He was the. This semester I took two. One is VLSI interconnects, and second one is digital circuits.
Okay.
Sarang, right? His name is Sarang. And VLSI interconnects, and all are IIT Kharagpur. Sorry, the last one is IIT Roorkee. This time it is IIT Kharagpur. Both are from IIT Kharagpur.
Okay.
I had a dream to pursue my graduation in IITs, but that was not fulfilled at that time. I was in Tier 2 college, but now I got an opportunity to meet all IITians or IIT professors, at least if I have some questions. So it's a great platform. That's what I felt.
Yeah, this is actually really good. I felt, and many of the NPTEL courses are like very good. I see the contents are also very good. Means,
Yes.
like, yeah,
It's close to industry.
correct. Yeah.
It's close to
The-
industry because I'm in the industry, so I can relate them. So how close these are? These are not theoretical.
Yeah,
These are
yeah.
more close industry. That's what I feel. Maybe upcoming 10-15 years, it is going to change entire the face of the semiconductor industry. That's
Yeah,
what I
yeah.
feel.
And India is targeting that, right? Like we need more workforce.
Yes, yes.
Yeah.
Definitely, India face is going to change, especially in the semiconductor industry for next 15 years. That's what I can predict. I can
Agreed.
see the progress also.
Yeah, yeah. And,
For this purpose, right, if you see more VLSI courses, it is related. And I want to know, so next semester I want to take two subjects. One is
Okay.
network circuits, and second thing is analog CMOS.
Okay.
That's what I'm planning. And in the so if you can provide me some insights, I mean your insights, maybe that would be helpful for me because
Okay.
if I go to NPTEL VLSI domain,
Yeah.
there we have some optional subjects.
Okay. Optional
So
subjects. Sorry, I didn't get the optional subjects part.
that if you want to become a NPTEL scholar, domain scholar, let us say, if it is electrical
Okay.
or VLSA, let us say it is a domain,
Okay.
in that you need to complete at least 4 core subjects.
Oh, okay.
Out of 4 core subjects, one of them,
Okay.
and basic electronics is second one of them,
Okay.
and third one is analog CMOS, you can take it,
Okay.
and fourth one is either microprocessor or microcontrollers, interfacing, or else you will be having one more option like microelectronics molding or something like that.
Okay. Okay.
So you need to finish all 4 will be one group actually. These are like mandatory subjects if you want to become any expert in the one field, let us say.
Okay.
So basic electronic graduate or electrical graduate can do all these things because he will be having his own curriculum in his syllabus, right? He will be having. And optional point of view, you can pick any 2 subjects.
Okay.
Out of them, VLS interconnects is one.
Okay.
One of them is optional subjects. And I have PLL architectures we have.
Yeah. Yeah.
And
PLL
and
is
mainly-
running this time, right? I think Saurabh sir is taking that.
yeah, PLL. Yeah, we want to learn the Saturday's architectures.
Okay.
I'm not sure which course I should take that.
I think
I
that
was
PLL
able to-
would be good. Means I took
Okay.
few lectures of. Means I attended few lectures there, so it was a
Okay.
very good course. I liked it. So maybe
Okay.
if it is being floated next time, then you can enroll that.
Yeah, maybe I think next year, this time only it will be enabled. I think in the June to December. That's what I feel.
Okay. Okay.
You know, the pattern if I see the number of courses, so which were floated in the January